Hello, everyone. Today we will start talking about digital modulation. Later on in this chapter, we will analyze some digital modulation schemes in terms of their performance on an AWGN channel. So the scope is not that wide, actually, because we have a very limited amount of time allocated to studying digital communication in this course. More of this will be in the following course, EE 436. However, we want to give a solid introduction so that you will understand the basic concepts of digital modulation and be able to analyze the bit error probability of binary modulation, one-shot modulation by the end of this chapter. And the related material is in chapter 8 of the textbook. So let's start talking about the concept that we call Emery-PAM. Emery pulse amplitude modulation. So binary stands for two possible values, as you know. Emery is a generalization of this, where we have m possible values for the signal. Right? So if you have m possible values, how many bits does this correspond to? Log to the base 2m bits. So in other words, if you have k-bit groups, okay, so if you have digital data that's coming into you, binary data already digitized, and you group these bits k at a time. Each of these k groups, for each of these k-bit groups, there are 2 to the k possibilities. Okay, so possibly if we find m different signals where m equals 2 to the k, then we could map each possible k-bit sequence to a signal, to a waveform. Okay, the idea is this in Emery modulation. Take 2 to the k possible bit sequences, map each of these to a distinct waveform. Now, if we do this in a way that basically corresponds to modulating the amplitude of a single pulse, modifying the amplitude of a single pulse, if we use a single pulse shape that is scaled in m different levels, that's one particular way of creating these m signals or m waveforms, and we call this pulse amplitude modulation. Okay, so we will consider this as the first thing we do. Later on, we say, okay, now our different waveforms do not have to be scaled copies of each other. What if they were different? What if they couldn't be represented as scaled copies of each other? In general, what if they contain orthogonal pieces to each other, or whether they're orthogonal to each other, or some are orthogonal to each other, etc. So in order to bring some mathematical structure to this, we will represent waveforms geometrically on a Hilbert space. You are already familiar with vector space concepts. And this vector space representation of waveforms is going to be very useful, because then we will be able to analyze error probability in very different modulation schemes using the same vector space model. And you will see that many different types of waveform families, they look different. They may map to the same thing on the vector space representation, which is going to make things easier for us. Okay. After introducing this machinery, we will then go to the specific case of binary modulation, for which we have essentially two waveforms, right? But those two waveforms can be aligned with each other, like the pulse amplitude case, or can be orthogonal to each other. We will see how these two cases are different. The orthogonal case is clearly where the two waveforms are orthogonal. The antipodal case is where they are aligned. But essentially, we're using two extremes. We will see the performance of antipodal and orthogonal signal schemes on the vector space and understand the pros and cons in terms of error probability and bandwidth use. And we will see some examples of actual modulation schemes like FSK, phase shift keying, binary PSK, that is, or amplitude shift keying, that are characterized as antipodal or orthogonal. And next, as the final thing we do in this chapter, we will consider optimal detection of binary waveforms. We will show that the matched filter is an optimal detector under AWGN. And we will analyze the error probability under optimal detection. Okay, now let's start by pulse amplitude modulation. And a very simple case, the binary case. In the binary case, k is 1, so we take 1 bit at a time. We're not grouping k bits at a time. We just take 1 bit at a time. And we, in general, in binary modulation, when we take 1 bit at a time, we will need two waveforms, right? Let's call them S1 and S2. All right. S1 and S2. Oh, okay. So now, as I said, in general, we take k bits at a time and use M-ary modulation using m, which is 2 to the power k waveforms. One example that we will discuss first is pulse amplitude modulation, modulating the amplitude of a pulse. Okay, binary pulse amplitude modulation. So pick a pulse, pick any possible, pulse g of t, okay? And in the simplest case, for example, you could consider the rectangular pulse example given here, okay, g of t. It's just a rectangular pulse that is constant at a level a from 0 to tb. Okay. Now, in the case of binary modulation with pulse amplitude modulation, we will use g of t and negative g of t. Okay, so one of them could stand for the 0 and the other could represent the 1. Okay, so to signal a 1, send g of t. To signal a 0, send negative g of t. Okay. In general, okay, if you have m signal levels and if you're using pulse amplitude modulation, you could use, for example, if m equals 4, you could use these 4 levels. Okay, take g of t and multiply its amplitude by the level a sub I when you're sending the ith possible sequence. We have 4 possible sequences when m equals 4. So in this case, 2 bits are transmitted at a time in this example. In general, log 2m bits are transmitted at a time. Now, incidentally, how do you obtain the mapping from bit sequences to signal levels, A1, A2, etc.? Last time when we talked about quantization and the subsequent digitization of data, we talked about different possible coding schemes. One of them was gray coding. We said gray coding was advantageous in the sense that successive levels, adjacent levels like S1 and S2, are separated by only 1 bit difference. Okay, so that enables us to make a small error in the case that one level is mistook for another. Why do we mistake a level for another at the detection, at the at the detector? Because of noise. So, for example, suppose -1 was transmitted. Oh, my pencil is failing for some reason. Suppose -1 was transmitted, but due to noise being added to it, we thought it is +1. Okay, so whereas A2 was transmitted, we detect A3. Okay, so A2 was transmitted, but we detect A3. How many bits will be in error? 1 bit. So that's the benefit of using gray coding. If you use natural binary coding, then it would be 0, 0, 0, 1, 1, 0, 1, 1. From level 2 to level 3, 2 bits would be in error, which is bad. Okay. Now, as I said, in memory modulation, we have m different waveforms. These are continuous signals, pulses, etc. And they can be in various shapes and amplitudes. But can we find a systematic way of thinking of these as vectors? Okay. Now, we will do this by mapping them as points in a Hilbert space. Now, how do you do that? First of all, I think the idea, it starts by taking our signal waveforms and seeing whether we can obtain an orthonormal basis for them. Okay. In order to obtain an orthonormal basis for our functions, we're going to apply the Gram-Schmidt orthogonalization procedure, which you may have seen before in other courses. Okay, suppose our family of signals are Sm of t, where m varies between 1 and m, 1 and capital M. Okay, how do we do this orthogonalization? Start with the first signal, S1 of t. Okay, and then convert it to a unit energy signal, X1 of t. So take S1 of t and normalize it by the square root of the energy. Okay, notice that our waveforms are finite energy signals. Okay, that's what we're assuming. Think of this pulse G of t, for example, has finite energy. Our G of t had amplitude A and duration TD, right? So, or TB. So the energy, right, is A squared TD. So in general, you can take S1 of t magnitude squared and integrate it. to compute the energy in S1 of t, and normalize by the square root of that energy to obtain a unit energy signal. I mean, clearly from this, gamma 1 of t has unit energy. That's the point. That's why we normalize. Next, we are going to obtain the second basis function by computing the projection of the second signal S2 of t on gamma 1 and taking the difference from S2. Okay, so what are we doing here? Compute the projection. What does that mean? Take the, well, we're talking about real signals for now, so no need to think about conjugates, complex conjugates. Taking a projection means taking the inner product. Okay, S2 of t multiplied by gamma 1 of t integrated from negative to positive infinity. And that is going to give us a scalar, which is essentially, if S2 was orthogonal to gamma 1, it would give us 0, right? If S2 was identical to gamma 1, it would give us the energy of S2. Right? So now, in any case, it's going to give us a number, and we will simply consider the difference from S2 of S2 from the first basis function scaled by this number. It's essentially the piece of S2 that is orthogonal to gamma 1. And I should stop saying gamma here. Phi 1. Okay, the part of S2 that is orthogonal to phi 1, our first basis function, is d2 of t, the difference. Okay. And we obtain the next basis function, phi 2 of t, by normalizing this difference. And we continue like this. Any questions? Okay. Now, so in general, we obtain the kth orthonormal signal or basis function by normalizing the orthogonal part of the kth waveform to all the other signals. That is, the difference of the signal from its projection on all the previous orthonormal signals or basis vectors. So what do? We obtain these coefficients or projections of the kth waveform on all the previous basis functions, phi I from 1 to k minus 1. Okay. And then what do? We say, I'm going to obtain the difference by subtracting from Sk the weighted sum of Cky phi I of t. And when I obtain this difference, I'm going to compute the energy of this difference function and normalize the difference function with the square root of that to obtain, by the way, this should have been E sub k, to obtain the kth basis function. Okay. Now, if at some step before or at m, if you find that the difference is 0, this means that this signal that you're looking at is not linearly independent of the previous ones, Hence, it introduces no basis vector. So as a result of going through all the signals, we obtain an orthonormal basis. Why orthonormal? Well, clearly they're orthogonal by construction, and they're normalized by construction because we're dividing by the energy. Okay, so we obtain an orthonormal basis of dimension up to m, dimension at most m. If all the m dimensionality of the resulting signal space would be m. Any questions here? Okay, let's see this in an example. Suppose S1, S2, S3, and S4 are given to us as a memory signaling scheme where M is 4. Okay. So let's see what kind of basis functions do we have for this family of waveforms. Now, phi1, what is phi1? Is S1 over square root of energy of S1. What is the energy of S1? 2, right? So S1 of t over square root of 2. That gives us phi1. Now we're going to compute the difference. d2 of t equals S2 of t minus C2, minus C2 phi1. Well, what is C2? C2 is the projection of S2 on phi1. Okay, well, S2 is this thing. Starts from 1 and it's one between 0 and 1 and equal to -1 between 1 and 2, and phi1 is this thing, constant at 1 over square root of 2. So what does that give us? Well, let's just write it down. From 0 to 1 we have 1 over square root of 2 dt. And from 1 to 2, we have 1 over square root of 2 times -1. So -1 over square root of 2 dt. Okay. So what does that give us? 0. It means that basically S2 is orthogonal to phi1. So in this case, D2 is simply S2 itself. Well, basically then phi2 is D2 normalized, which is D2 divided by the energy. Energy is again the same, square root of, well, energy is 2, so S2 divided by the square root of 2, and that gives us our phi2 of t. Okay. How about phi3? Well, now I'm going to have to consider the projection on on phi1 and phi2. So let me erase all of this. And write down phi3 is going to be d3 divided by square root of the energy of d3. And d3 is S3 minus C1 phi1 minus let's just say C3 2 phi2. You understand C31 is the projection on phi1 and C32 is the projection on phi2. Well, what is C31? It is S3 times phi1 dt. What is S3? S3 is equal to -1 from 0 to 1, and then +1 from 0 to 3. Okay, so, and phi1 is here. So the integral goes from 0 to 1 as 1 over square root of 2 times -1, plus from 1 to 2, phi1 times S3 is 1 over square root of 2. Well, what did we get? We again get 0. So this term is gone. How about C32? C32 is S3 of t times phi2 of t dt. Phi2 is here, 1 over square root of 2, -1 over square root of 2. Okay, now we're going to get some positive inner products. From 0 to 1, we have -1 over 2 square root of 2 dt. And from 1 to 2, we have again -1 over square root of 2 dt. As a result, we have -1 over square root of 2 plus -1 over square root of 2, which is square root of 2 over square root of 2, which is negative square root of 2. Okay, let's plug it in this expression here. D3 of t equals S3 of t minus negative square root of 2 times phi2 of t. Now, so plus square root of 2 phi2 of t. What is phi2 of t? It's here. So if you multiply by square root of 2, you get 1 minus 1. Add that to S3. Add 1 minus 1. What do you get? You get essentially, let's just draw it here. This is 1, this is 2, basically this. 1 plus 1 is 2. And then, so this is D3 of t. And then energy of this thing, E3, is equal to 4. So phi3 of t is D3 over square root of E3, which is D3 over 2, which gives us this normalized waveform. Okay. Now let's see what will happen with the fourth waveform. Clearly, by inspection, the fourth waveform can be obtained by scaling phi1 by square root of 2 and adding to it phi3. So let me write it here. S4 of t equals square root of 2 times phi1 of t plus phi3 of t. So clearly, S4 is a linear function of the previous orthogonal waveforms. So the previous basis functions. So it's not linearly independent. Then clearly D4 is going to be 0, resulting in no new basis function arising from the fourth waveform. So in summary, from an original set of M waveforms, we obtained 3 orthonormal waveforms, and they are phi1, phi2, and phi3. Now, we can go to a vector space representation. Once you have a basis, you know how the rest works. Every other function can be represented as a point in this vector space, spanned by these basis functions. So each signal can be represented as a vector formed by its projections along the 3 basis functions. Okay, we have a signal space of 3 dimensions. In this example, these 3 basis functions give us a vector space of 3 dimensions, and any other waveform that we add can be represented in terms of their projections on these basis functions. So in general, if you have an n-dimensional vector space and you're adding a new signal to it, you can represent the signal in terms of the projections along the n different basis functions. Okay. And when you do that, there's going to be some cool properties that are going to arise. First of all, the inner product of the original functions of any 2 original functions is equal to the inner product of the corresponding vectors. What is the inner product of the corresponding vectors? What we mean is this SM dot product SN. What is this? This is basically SMI, SNI, sums I from 1 to n. Okay. Another result that follows from this is that you can compute energy, as you know, we compute energy by doing what? Taking the inner product of the signal with each other, with itself. Okay, but because of this, as a corollary of this result, by the way, I would like you to show this result. It's very simple to show. By a corollary of this result, the energy of a waveform can be computed from this vector representation as the squared Euclidean distance from the origin. Okay, so substitute m equals n. Sm squared equals Sm I squared I from 1 to n, which is the distance from the origin. Okay, so basically when we represent our signal S, okay, Sm as a point in the vector space, the energy is the distance of this point to the origin. Okay. Now, when we are given a set of n functions, the choice of the basis vectors for this set of n functions is not unique. Depending on which order you start normalizing, orthonormalizing the signals, that is, in which order you run this Gram-Schmidt procedure, you may arrive at different sets of basis functions, but this does not affect the dimensionality of the space, the length of the vectors representing the signals or their inner products. It just changes the shape.